Thank you. Boy, I wish I still looked and felt that way. That's good. Years old. Thank you. Well, first of all, let me just say what a great pleasure it is to be in Taiwan. I have a long history in Taiwan. My first visit here was in the spring of 1971. And I was on my way from India to Hawaii to start working on dengue viruses with Scott Halstead and Leon Rosen at that time. And so I've been involved with working in collaboration with Taiwan scientists ever since. Sometimes more than others, but always working together. I didn't really know the focus of this program when I sent this title, but I think it's going to be appropriate in any case, because to control dengue, we've got to control epidemics. And the issue is whether we can eradicate dengue or not. I don't think we ever will, but we can control epidemics. We can control epidemics. We need to understand epidemics. And so my talk today is really about what we know about the cause of epidemics. Okay, you've all seen this slide. It's been published many times, but I use it to illustrate, remind you of the history of dengue with the beginning of emergence of epidemic dengue in the late 50s and 1960s, but the acceleration of epidemic dengue in the 1970s and 80s when jet air travel became common. And since then, it's been a continuous upward trend of the incidence of dengue. But the thing I want to point out to you is that dengue epidemics are cyclic. They occur depending on the country you're dealing with every 3 to 5 years, sometimes more, sometimes less. But on a regular basis. We don't really know why that type of a cycle occurs. And this just shows some Asian countries, the cyclic nature of epidemic dengue in Indonesia, Thailand, Sri Lanka, and India. Dengue epidemics are also seasonal. If you look at the transmission of dengue in any endemic country, epidemics and increased transmission in non-endemic years always occurs, or almost always occurs, during the rainy season. In the countries above the equator, that usually is between June, July through October, November, depending on the year. And to illustrate this, the 3 epidemics in Puerto Rico, between 1998, 2007, and 2010. Basically some variation, but always during the rainy season. If in countries below the equator, this rainy season usually occurs in the first few months of the year, usually from November, December through about April. And epidemics in the southern hemisphere almost always occur during that period of time, from January to April. So you can bet the farm on that. You know that this is when seasonal transmission is going to occur. And also diseases like Zika, which are transmitted by Aedes aegypti, and yellow fever, if it ever occurs, will probably also, because it has really to do with the bionomics of the mosquito vectors and their survival. So the question that we want to address is, well, just to refresh, the dengue epidemics are cyclic, they're seasonal, they're often focal in nature, they don't always spread throughout the entire country, and they vary in severity. I'm having a hard time with this. They vary in severity both clinically and epidemiologically. So the main question that we have then is why? What is the cause of epidemics? Do we think we know the answer to this? For 50 years we focused on the explanations relating to herd immunity and to mosquito population density. But it's much more complex than that. There are many times when mosquito populations are very high, herd immunity is very low, and there's no epidemic, even though the viruses are circulating there. So the question is why? And I've just listed some of the other factors that influence epidemic transmission. Herd immunity is certainly important, don't get me wrong, but human population density, i.e. the urban growth that we've seen, has had a tremendous impact on epidemic transmission. Human behavior, that then relates to the standard of living. In areas where you have hermetically sealed houses that are air conditioned and television, you don't see very much dengue. You see sporadic cases, but it's not major epidemics. In countries where the houses are open, not screened, not air conditioned, would allow the air to move through, that's where you see most of the dengue. Mosquito population density is certainly important. Changes in the mosquito vector competence is important. We know that this is genetically controlled as well. You can, if you have a strong drought, you can bottleneck your mosquito populations, and the mosquito populations that emerge from that drought may be completely different in terms of their ability to become infected and transmit dengue. We don't understand this, but we know that it occurs. The introduction of new serotypes we know can cause epidemics, but it's not uncommon to have new serotypes introduced into a population, even if that serotype hasn't been there for many years, and it doesn't cause an epidemic, not immediately. And changes in the dominant serotype. We know that viruses that are circulating over a period of time, the dominant serotype that is causing disease there changes from year to year to year. And then we come to the topic of this talk, change in viral fitness and epidemic potential. Of course, all of these influence transmission dynamics and influence whether or not there could be an epidemic. What we don't know is what combination of these factors are critical. And I would probably guess that this depends on the ecology, the epidemiology, population dynamics in the different countries. So there's probably no one size that fits all here. It's a very complex issue. Another related question is why do we have see epidemics that vary in their severity? Some epidemics are explosive, move through the population like a wildfire, causing a lot of severe disease. Other epidemics are more what I would call smoldering. They just move through the population on a slow basis. For 50 years, we focused on herd immunity and immune enhancement as the major factors relating to epidemic transmission and to disease severity. Age of population is also important. Pushing the wrong button here. What we've ignored for 50 years are the possible changes in the variation in the viruses that cause these epidemics. And in 1971, Leon Rosen and I actually studied epidemics in the South Pacific that suggested that the virus did change genetically. But you have to remember, in 1971, we didn't have the molecular tools. We had no idea what dengue viruses were like in terms of their genome. And so it was purely speculation based on epidemiologic data. But certainly we now know, after all of these years, that genetic changes in the viruses influence fitness and infectivity, both in humans and in mosquitoes. Influences epidemic potential, it influences virulence. Another factor that we don't really fully understand is the genetic background of the human population, and this is more in relation to severe disease probably than it is to epidemic potentials. So this is the area that I'm going to focus on, and basically the fact that over the past 20 years essentially we've seen accumulating evidence that the variation in virus fitness and infectivity, epidemic potential, is much more important than we ever anticipated before. So what I want to do is use some of my studies. These are 4 case studies that I worked on over the years, and I've got a lot of collaborators in these work. I've put the references at the end of this talk so that you can see who the collaborators are, but there are too many to list. But basically, these four case studies each had epidemiologic data suggesting that there was something unusual about the viruses that caused those epidemics. So what I want to do is I'm not going to talk about Indonesia here because I don't have the genome, the sequences fully finalized on that. We're getting close to writing it up, but it's not complete, so I won't talk about it. But I will talk about these 3, South Pacific, Sri Lanka, and Puerto Rico, all of which are fairly well complete now. So begin with the earliest one in South Pacific. The South Pacific are remote islands. They were pretty much isolated for 25 years after World War II. There was a big Dengue 1 pandemic that moved through the South Pacific in 1944-45. Then the virus disappeared. So the viruses, none of these islands had endemic dengue. The exception is Tahiti that had Dengue 3 introduced to Tahiti in 1965 from the French West Indies. It caused small outbreaks in 65 and a small outbreak in 69 and then disappeared. But the rest of the islands were naive. They hadn't seen dengue since 1945, approximately 25 years. The primary vector in all of these islands is Aedes aegypti, but all of them have Scutularis complex species that belong to the subgenus Stegomyia, very closely related to Aedes aegypti and Aedes albopictus. The host genetics of the human population is relatively homogeneous in all of these islands. And in 1971, the American genotype, what I call the French connection, was introduced into Tahiti again from the French West Indies. And it caused a massive epidemic, a severe epidemic. Almost simultaneously, severe epidemics in Tahiti and in Fiji. Shortly thereafter, in late 71 and early 72, a severe epidemic in New Caledonia. And all 3 of these epidemics were associated with severe disease and deaths. There were several deaths in all of them. We were able to study every one of these, and we have acute sera, so we were able to isolate the viruses. We couldn't do anything with the viruses in 1971, 72, so we just inoculated them into mosquitoes and put them in a -80 freezer and forgot about it until we had the molecular tools to look at it. But the interesting thing about this story is that another severe epidemic in Niue that had just blew through the population, nearly a 90% attack rate, and a lot of severe disease and death associated with it. Unfortunately, I was in Samoa at this time, and I couldn't get to Niue, so we didn't get a virus out here. So we can't really say too much about the Niue, but epidemiologically and clinically, it was dengue shock syndrome. They killed a lot, and these were primary cases of dengue. So this was the first time that Leon Rosen and I questioned Scott Halstead about ADE. Something is wrong here. This doesn't fit the picture. And the interesting thing about it also is Tonga, sitting right here in the middle of all of this, had no dengue. And for 3 years, we watched for Tonga to take off, and it never did. In January of 1994, a colleague of mine from Johns Hopkins was on his way to Tonga to study filariasis. So I asked him to go to the hospital and see if he could find any dengue-like illness. A couple of months later, he sent me 8 paired sera, and 4 of those paired sera seroconverted to dengue 2 by neutralization test. So we thought, wow, we've got an epidemic going in Tonga. So I loaded up all my gear and headed out to Tonga. I spent 6 weeks in Tonga looking for dengue. I couldn't find it. I would have to get up early in the morning and go to the hospital, go to the outpatient clinic, and go through their log and So what I did is I picked out patients who had fever and any other non-specific syndrome. Then I would get my mini moke and I would go to their house and I bleed them and I fed mosquitoes on them. And for 6 weeks I did this. I found only 20 cases of dengue. And I was able to isolate the virus from 6 of those cases. And none of those cases had enough virus to infect mosquitoes. I actually fed mosquitoes. So that was a puzzle to us. Something was different about this Tongan virus. And again, though, we didn't have the tools to answer that question, so we put them in the freezer and essentially forgot about it. But when we got when genome sequencing came online and became common, we dug all of these viruses out of the freezer and had to sequence. And this shows the dengue 2 genotypes: Asian American, cosmopolitan American, Asian 2, Asian 1, and the Sylvatic down here. You'll note, and you can read this, but all of these South Pacific viruses that we isolated from Tahiti, Fiji, New Caledonia, and Tonga fit into this American genotype, and all of them were the same plate. Basically, they look identical when you look at the envelope gene. But when you do full-length sequencing, you get a different story. Turns out that all of the viruses from Fiji, New Caledonia, and Tahiti were in a separate place from the Tongan virus. All of the Tongan viruses that we sequenced were there was a lineage change, and they were completely different. There was one Tahiti virus up here that fit into this. I'm not sure if this was the progenitor virus or not. But the point is there was a lineage change in that virus that attenuated it. Didn't make it more severe or more fit. It actually attenuated it and allowed the virus to cycle silently in the population without detection. As we looked at this, there was one change in the PRM and a change the amino acid change in the 2A and the 4A. And those were the only changes in the genome, but it was consistent. So we hypothesized that those 3 amino acid changes actually changed the phenotype of this virus and made it more of an endemic type of virus. So next case study is Sri Lanka. Sri Lanka has had a history of dengue for many, many, many years. It was confirmed actually in the early 1960s serologically, but they didn't have any capability to do virus isolation. Dengue hemorrhagic fever was rare or non-existent. We didn't know of any dengue hemorrhagic fever there. So the question in the late 70s was, Scott Halstead and I were at a meeting in New Delhi, and the question, why aren't we seeing dengue hemorrhagic fever in Sri Lanka? Because all 4 serotypes are circulating there. There should have been dengue hemorrhagic fever, and there was not. So I went to Sri Lanka in 1977 to help Peace of Atana set up his virus isolation system and start surveillance. And basically this shows the history of the dengue in Sri Lanka. I showed up back here in 1977. By 1980-81, we were isolating viruses. And so we were able to isolate dengue viruses all during this early period in Sri Lanka. The Tamil War really took off in the late 1980s, and it shut down the whole program. So we didn't get any viruses in the latter part of the 80s at all. There was one epidemic in 1982, which was a dengue 2 epidemic, mainly secondary dengue infections. They were all mild. There wasn't a single case of dengue hemorrhagic fever that's in the Colombo area. In 1989, another epidemic occurred, and this time there was dengue hemorrhagic fever associated with it. They didn't have the facility to isolate the virus, so they packed them up and sent them to me in Puerto Rico at that time. And I isolated the virus. Turned out that it was all 4 serotypes were circulating there, but the dominant serotype was dengue type 3. And over the next few years, there were sporadic cases of dengue hemorrhagic fever, then a series of epidemics in the early 2000s that were associated with a lot of dengue hemorrhagic fever. And during this time also, the dengue viruses began to spread throughout Sri Lanka. Till today, basically, the whole of the island is now hyperendemic with dengue and dengue hemorrhagic fever. But the interesting thing is looking at the genetic tree here, the phylogenetic tree of these dengue-3 viruses. We have isolates from the pre-1989 viruses here, before the epidemic of dengue hemorrhagic fever occurred. We had isolates from the post-1989, from 1989 and into 2000 here, and then in the early 2000s, isolates here. So what happened was this lineage here actually changed to cause this epidemic, and then changed again to cause another epidemic. No evidence of any introduced virus. This was strictly a lineage change within the viruses that were circulating in Colombo. Aravinda de Silva and Bill Messer did most of the sequencing for me. But this was the case again. I had taken the viruses in the early 1980s and just put them in the freezer and forgot about them. So I had these viruses that I could pull out of the freezer that were essentially wild-type viruses, just like they were in the early days, and was able to compare them with the current isolates. So again, Sri Lanka basically shows a similar type of lineage change associated with epidemic. Puerto Rico is my last example, and this just shows the history of epidemic Puerto Rico in an island that didn't have any dengue in the 50s, but in 1963 there was an epidemic of dengue-3 that occurred there. This was the virus that was introduced into Tahiti in 1965. In 1969, an epidemic of dengue-2, and this was the virus that was introduced into Tahiti in 1971. Dengue, in 1977, there was an outbreak with both of these viruses circulating, but dengue-3 was the dominant virus. 1978, dengue-1 was introduced and caused a big epidemic, but it was still dengue fever, no dengue hemorrhagic fever during any of the time. In 1981, dengue-4 was introduced and caused an epidemic in 1982 that dengue-1 and dengue-4 were both transmitted, but dengue-4 was the dominant virus. Again, only dengue fever was observed. 1984, dengue-2 was introduced into Puerto Rico, actually from Cuba. It's the same virus that was caused the Cuban epidemic in 1981. And so we thought we were going to have an epidemic of dengue-2. Didn't occur. We had the epidemic, but the epidemic was dengue-4, not dengue-2. And it was associated with dengue hemorrhagic fever. The first fatal case in Puerto Rico was a dengue-4 isolate from a 30-year-old female. In 1994, there was that epidemic of dengue-2 occurred almost 10 years after it was introduced. It caused a major epidemic of dengue hemorrhagic fever. And in 1997, dengue-3 was introduced into Puerto Rico, and this was the genotype 3 from Indonesia, or from Sri Lanka and India that was introduced. So we thought we were going to have a big epidemic in 1998. In fact, we did, but it was not dengue-3, it was dengue-4. And dengue-3 ultimately then caused an epidemic in 2001. Not a large epidemic, it caused the epidemic, and then another one in 2007. But the point is interesting sequence of events here. We're not sure yet exactly what it all means, but clearly it's associated with hyperendemicity, the evolution of these epidemics. So this just shows it in a different way. Shows a different epidemic beginning in 1986 here, 1994, 1998, and some subsequent epidemics. Shows the viruses down here. This was dengue-4. This one was dengue 2, and this one was also a dengue 4 epidemic. But there were other viruses being transmitted at the same time. So let's look at these two epidemics here, the 2 dengue 4 epidemics. And these are sequence data done by Shannon Bennett and her group at the University of Hawaii, now at the University of California. But basically, this shows the phylogenetic history of dengue 4 in Puerto Rico. If you look here, this is clade 1. This is the virus that was introduced in 1981 and caused the 1982 epidemic of dengue fever, not dengue hemorrhagic fever. There was a clade change sometime that occurred between 83 and 86, and this clade change, or lineage change, led to another clade of dengue 4 virus we call clade 2, and it was the one associated with an epidemic of dengue hemorrhagic fever, with dengue 4 as the dominant virus. Then another clade change from this to this, and this is the virus actually changed, more like Tonga did. It went underground. It was sporadic transmission for over 10 years with no epidemic. But it was still there, and we were able to isolate it from cases. But then a final clade change in the late 90s that actually was associated with another epidemic of dengue 4 that was associated with dengue hemorrhagic fever, clade 5. And this next slide just shows the sequence, how this moved through the islands. Each one of these areas, the little lines, are what we call municipalities in Puerto Rico, and each one is unique politically and geographically. The clade 1 viruses show up here. We didn't isolate a lot of viruses or sequence a lot of viruses from 81, 82, but they were all belonging to clade 1 when we did. Sometime in late mid-80s, a second clade evolved, clade 2, which is shown here in magenta, and spread throughout the island. Late in the 80s, clade 3 emerged in the San Juan metropolitan area, and it spread throughout the island. This is the virus that was associated with no epidemic. And then another lineage change with clade 4 emerging again in the metropolitan area here and spreading throughout the island. So again, our conclusion was that it was this lineage change that was associated with the epidemic transmission. So now look at the dengue 2 epidemic that occurred in 1994. We sequenced these viruses. Basically, you see here the virus that had been circulating since 1994, 1984 was what we called a lineage PR1, and it was circulating for almost 10 years. Then an epidemic occurred in mid-1994, in the summer of 1994. When I took these viruses to Singapore with me, and then we ended to sequence them. And basically, you see that there was a lineage change here. And the epidemic was actually associated with the PR2 lineage of the virus. And Young developed a slide here that sort of summarizes all this. I don't have time to go into it. But the bottom line is that there were 3 changes in the 3' and untranslated region of the virus. And those 3 changes led to an increase in viral subgenomic RNA in those patients. And in Young and his group did the molecular biology to show that subgenomic RNA suppressed the interferon response in those patients, resulting in higher viremia levels and infectivity. This just shows, and I won't take the time, I'm running out of time, to go through all of this, but the essentially, this is the interferon. You can see the higher interferon in the PR1 versus the PR2 in every one of these. And these are human liver cells, and these are monocytes. And the ratio between genomic RNA and subgenomic RNA is shown here. All of the PR2 viruses had a much higher ratio of subgenomic RNA, and that resulted in a decrease in the reduced interferon level. It's another cartoon that basically shows what happened to here. The subgenomic RNA here actually inhibited the TRIM25, which then led to reduced interferon. And interestingly, there's a paper just recently published by Manuel Noriega from Brazil, which shows a similar type of response. But it didn't affect the immune response, or he didn't report on the interferon response. It affected the immunogenicity of the virus in the humans. And the humans, because low immunogenicity allowed the virus to spread more widely in the human body, and resulted in higher viremia levels as well. But it underscores the complex physiology that we're dealing with here, the interaction between the virus and the human host. So in conclusion, epidemiologic, sequence, and molecular biology data from 3 dengue serotypes, dengue 2, 3, and 4, isolated from epidemics in 3 countries, in 3 geographic regions, show a close correlation between small genetic changes in viruses and phenotypic expression in humans and mosquitoes. The phenotypic changes included clinical severity and viremia levels in humans, virus replication in mosquitoes, and cell culture, inhibition of interferon expression in vitro, and changes in epidemic potential. And the data suggests that dengue virus evolution via drift and positive selection result in the emergence of new viral lineages of the same genotype that play an important role in the epidemiology and pathogenesis of dengue disease in humans. And we all know that epidemic potential, disease severity, and pathogenesis of dengue are determined by a complex interaction of viral, host, and environmental factors. So I would hope that we would start looking at some of these complex interactions to identify areas where we could interrupt transmission. And just a final slide or two here. The previous infection, herd immunity, immune enhancement, don't get me wrong, it is important, it occurs, we just don't know, well, at least in my opinion, it's not as important as we have thought for 50 years, that the genetic changes in the virus, the influence of these genetic changes is probably equally or more important than ADE. And of course, a big unknown is the influence of the genetic human population. This relates more to disease severity probably than to transmission dynamic. And so disease severity, basically, the risk factors, everyone lists previous infection, and ADE is the main one. I put virus strain on top because I feel the virus strain is probably more important because not all viruses can be enhanced, and not all antibody enhances antibodies. So it has to have something to do with the strain of the virus. And of course, previous infection, age, and host genetics are all important. So at the end of the day, I still think, and I actually published this in 1994, I still think hyperendemicity is the key to determining whether we're going to have enhanced severe disease. And it's compatible with both theories of virus virulence and immune enhancement. If you've got hyperendemicity, it leads to increased probability of secondary infection, increased probability of immune enhancement, and increased probability of DHF. Likewise, if you've got hyperendemicity, it leads to increased transmission and the movement of viruses into new areas, increased probability of genetic change, positive selection, and emergence of viruses with greater epidemic potential. And it's those epidemic viruses that are most frequently associated with severe disease. And that also leads to increased severe disease. And so this is just a list of the publications, and Oscar has these. So this is this recent paper here by Pinheiro and Mari in Brazil. Because it basically shows the same thing. There's another paper here. All the rest of these are our papers, but this one here by Eva Harrison's group in Nicaragua also shows a similar change with dengue 2 in Nicaragua. So with that, I'll quit. Thank you very much.